This lecture deals with multiple regression. Key topics include standard errors, t-values, p-values, multiple independent variables, nonlinear effects, and dummy variables for nominal and ordinal measures. So what exactly is multiple regression? Well, up until this point, we've been looking at linear regression equations that involve only a single independent variable. Now we're going to be looking at multiple regression models that involve using two or more independent variables. So we can write the linear regression equation for the predicted value of the dependent variable as follows. We have y hat, the predicted value of the dependent variable, on the left-hand side of the equation. And then we have a set of independent variables and an overall model intercept on the right side of the equation. And so on the right side of the equation, we have beta 0, which is the model intercept, plus the effect of beta 1 times x1, which is the slope effect, beta 1, times the value of the first independent variable, x1, plus beta 2, the slope effect of the next variable, x2, all the way to beta p, which stands for the last independent variable in our model, the one corresponding to p parameters. So multiple regression is a flexible methodology that's widely used in the social and behavioral sciences. And in this lecture, I'm going to be using an example of multiple regression using data from the 2012 General Social Survey, which will be a random sample of 350 cases. As an example, we're going to be looking at the relationship between father's education and response education. And again, suppose that we were interested in testing some kind of a theory of status attainment or the transmission of educational advantage or disadvantage across generations of family members. The scatter diagram shown in this slide relates father's education as an independent variable, which is arrayed along the horizontal or x-axis, to the respondent's education, which is the dependent variable, which is arrayed along the vertical or y-axis. The scatter diagram also shows the values for all 350 points used in the analysis, which basically graphs their relative location of father's education against respondent's education. And so if we're looking at the pattern here, we can see that as father's education increases, so does the response education. In other words, there's a positive relationship between father's education and response education. More educated fathers tend to have more educated children, and vice versa. So we need some kind of more systematic way to look at the relationship between fathers and response education. And so we can estimate the simple regression of that relationship. And so table 1 here shows some of the output for regression analysis using the simple regression of education against father's education. And so we start with the beta coefficients, the slope and intercept effects. Here is our intercept. It tells us that the value is equal to 9.83, and it's interpreted as the predicted value of education for somebody whose father has 0 years of education. So that person is predicted to have just under 10 years of education, or 9.8 years specifically. Here's the slope effect of father's education, beta 1, and it basically tells us how much the response education is predicted to change as we change the value of the father's education. And so for every year increase in father's education, we see that we have a 0.53 year increase in response education. In other words, every time the father gains a year of education, the respondent is predicted to gain just over a third of a year of education. The standard errors basically tell us something about the variation across samples in these estimated regression coefficients. And so to think about that, imagine that there's some kind of a population from which the sample of 350 cases was drawn. And if we had the information on the entire sample, we would get the actual value of father's education on response education and the actual value of the intercept. But instead what we have is some sample data that's based on a subsample of cases. And so for this subsample, the values are slightly different from what we find in the population. In fact, if we took repeated samples, we would find that each of the sample results would differ slightly from the population results. And so the standard error is basically accounting for the amount of variation in the sample results across different samples. We can use that as the basis for doing some kind of a test to see whether the sample results relate in some way to what we think the values might be in the true population. And really the t-values and the p-values that I'm going to talk about next are the two things that we use to make those generalizations. And so typically what we're interested in is we're interested in testing whether these regression coefficients, both the slope effect of father's education and the intercept, are different from 0 in the population. And the t-value here is basically telling us the distance in standard error units between the actual value of father's education that we get in this sample, 0.35, and its assumed value in the population, 0. Its t-value, 10.31, basically says that if the true population slope effect for father's education is 0, then this sample result is over 10 standard deviations away, and that's a pretty unlikely result. The degree to which it's likely or unlikely is expressed by this value p, which is a p-value. And it basically tells us how likely it is that we find this particular sample result, given what we think are the true values of the regression coefficients. And so if we think that the father's education has a non-effect in the population, that is, it's 0, we would hardly ever find this sample result by chance alone. And so what we're looking for is a value less than, say, 5%, something less than 0.05. And if we find that something occurs less than 5% of the time, that is, its p-value is less than 0.05, we would say that this result doesn't happen by chance alone. There's something systematic about it. Another way to write the simple regression is basically to get rid of the t and p values and substitute in their place a series of asterisks or stars. And so notice that the regression coefficients here have 3 stars next to them. And so if you look at the bottom of the table, which includes a key, it basically tells us the p-values corresponding to those things. And so in this case, the 3 asterisks or stars indicate that these regression coefficients have a p-value of less than 0.001. In other words, they occur less than 1 in 1,000 times. And so this result doesn't happen by chance alone. It's likely to be a statistically significant and hence systematic effect. Okay, so why exactly is it a good idea to add multiple explanatory variables to a regression model? Well, sometimes having a single independent variable isn't sufficient to represent what's going on in the real world. And so if we add additional independent variables, we better isolate the effects of those variables that we're most interested in. And so in the next example, I'm going to add another control variable, another independent variable. I'm going to add age to the model. And so notice that when we add age to the model, our scatter diagram is no longer a 2-dimensional scatter, but a 3-dimensional scatter. And so now we can graph each point according to its location on father's education, response education, and age. And so now a regression line is no longer sufficient to model the relationship between education and father's education. Because we've added another variable, we've added another dimension to our data, and now we need a regression plane. And so notice that we also increase the amount of error that has to be explained, because not only does error have to be explained on one dimension, father's education by response education, but we now have to do it on another dimension, age and response education. And so the preceding figure basically showed us that we had a 3-dimensional scatter diagram with 3 axes. On the x-axis was father's education, on the y-axis was response education, and on the z-axis was response age. And so in general, adding more variables to the model increases the dimensionality of the data. And it's a little hard to imagine anything beyond 3 dimensions. But basically, the number of dimensions is equal to the number of independent variables we add to the model. Let's take a look at some multiple regression output now. And so here we have 2 models. The first is our original model, the simple regression of father's education on response education. And the second model that we've added directly to the right of that model is the one that includes a value for age. So notice first that there's a slight improvement in model fit. So whereas the first model explains 23% of the variation in education, the next model has a slight improvement in model fit. And so together, age and father's education explain about 24% of the variation in response education. And we can also see that the slope effect of father's education changed slightly. So it increases from 0.35 to 0.38. And the question is, why did it change? Well, in the first model, basically what's going on is that the effect of age, which is left out of the model, is being captured somewhat by father's education. And in the second model, which explicitly includes a measure for age, what we see is that father's education is now net of the effect of age. In other words, we've isolated the effect of father's education from age. And so we can see how much an effect each of those has independent of the other. Now, note that the interpretation doesn't change very much. We'd still interpret father's education in terms of a unit increase in it. And so for a unit increase in father's education, we're still predicting some value for the response education. This time, we're predicting that response education increases by 0.38 years. But now we have to specify that that's net of the effect of age. In other words, we've statistically controlled for the effect of age and the effect of father's education. Now, suppose that we thought that there was some kind of a nonlinear association between a given independent variable and a given dependent variable. In general, regression coefficients measure the linear association between the two. But what if we thought that there was no linear association? Suppose that we thought that increasing values of age, for example, would track with increasing values of education up to a point and then start to decline. Let's take a look at the scatter diagram showing the relationship between age and response education. Notice that at the low values of age, that is people in their 20s and maybe early 30s, what we see is that age increases, education also increases. And notice that at the other tail of the distribution, what we find is that people who are older have lower values of education for increasing values of age. So here, a linear function would not be a good fit to the data. Instead, we probably ought to use some kind of a curvilinear, perhaps inverted U-shaped function that captures the increasing effect of age and education at early years of age and the decreasing effect of age and education at later years of age. And so what we should do is we should try to model that curvilinear relationship somehow. And so we do that by adding something called a second-order polynomial, or a squared term. This literally is another variable in our model that's equal to the number of years that each respondent has squared. And so when we add that variable to our model and we add a slope parameter to it, the effect of age on education is going to be actually captured by two coefficients. The first will be the main effect of age, and the second will be the squared effect of age. And these two should be interpreted together. And so notice that I have a third model in this table. The third model includes not just the main effect of age, but also effect of age squared. First, notice that there's another slight improvement in model fit. So collectively, the effects of father's education, age, and age squared now explain 26% of the variation in age. We can also see that the slope effect of father's education changed somewhat, and as did the effect of age. And so we can see that father's education declined a little bit, although it's largely the same. And we can see the effect of age changed appreciably. So rather than having a 0.018 effect, now it has an effect of 0.15. However, we have to interpret the effect of age and age squared together. And so let's consider how to do that. Notice that the main effect is positive, but the squared term is negative. Notice also that the squared effect is a lot weaker than the main effect of age. And so how does this combination of coefficients and variables work to create a curvilinear effect? Well, for one thing, the main effect is stronger than the squared term. And so the natural question to ask is, what happens as age increases? Well, as age gets bigger and bigger, notice that the squared term gets more and more influential. It gets bigger and bigger in size. And so at low values of age, the large positive main effect of age is the one that's the more significant in the equation. But then at bigger effects of age, as age gets bigger and bigger and bigger, the squared term starts to become more and more influential on the effect of age on education. And so eventually the positive effect that's found at the low values of age starts to bend down. And so the curve starts to take on more of a curvilinear appearance. And so here is the scatter diagram of age and education in which I've superimposed the response curve for the effect of age. And so notice that it's a inverted U-shaped pattern. Basically, at low values of age, we see that the effect is somewhat positive. But then we reach a point, and the age effect starts to decline into the old ages. And so what we have here is basically an inverted U-shaped curvilinear function, which we can easily incorporate into a multiple regression model. Another thing that we can incorporate is ordinal and nominal variables. And we do that by turning them into a series of dummy variables, that is, variables that are coded 1 or 0. And we have a separate dummy variable for each category of the variable, except for one that's left out, which is a reference category. And so consider a variable like sex, which in the GSS is measured as 1 for males and 2 for females. We can actually recode this as a dummy variable. Let's code males as 1 and females as 0. Well, that would be called dummy coding. And so what we're left with is a variable that's equal to 1 for men and 2 for, or 0 for women. Before we add that to a regression model, let's actually take a look at the descriptive statistics on that variable. And let's look at the different distribution of education for men and women. And so the following figure shows a box plot of education separately for men and women. So notice that the distributions are largely the same. There's some slight differences here. We can see, for example, that the median for men is a little bit lower than that for women. We can also see that the minimum for women is a little bit lower than for men, although the values of the minimum for women are largely outliers. And so, in general, the two plots look very much alike. They're very similar. There's only minor differences in a slightly lower median for men and a bit lower value at the minimum for women, which is an outlier in this case. So we can just add sex, which we should probably call male because the value of one of that recoded variable is equal to male, into our regression equation, and that's shown in the next slide. Now note that there's no need for separate variables for men and women. The coefficient for male is in reference to the omitted category, women, and it shows basically the average difference between men and women with respect to their education, net of all the other factors in the model. And so here I have basically just two regression models. The first basically shows our last model with father's education, age, and age squared. And the new model, directly to its right, is the one that includes the coefficient for male. And so again, we see that there's a slight improvement in model fit. The combination of father's education, age, and sex, male in this case, explain 27% of the variation in the dependent variable. Notice also that we have an effect for male, which is here relative to the omitted category, female. And so we can see that on average, men have about 0.62 years less education than women. So women are slightly more educated than men, net of their age and their father's education. What if we wanted to add a variable that has multiple categories? For example, something like race. The GSS measures race using 3 categories, white, black, and other. And so we can basically make 3 separate variables, one for each of these categories. But we have to make one of them in the omitted reference category. So, for example, why don't we choose white as the omitted reference category? The box plots show differences in education across the different races. So we have a different box plot for whites, blacks, and others. Notice that the education effects are largely similar, although it seems that, at least for the other category, there's a more narrow range for the middle 50% of the data. The max and min, not considering the outliers, is also a little bit more narrow. And so the distribution of education seems pretty similar across racial groups, although there may be some slight differences from the other category, from whites and blacks. The group has a slightly lower median also, and more outliers at the tails. And so here is some more regression results. Here I've included just 2 models again. The first one is the one we just looked at previously with the male coefficient added. This one adds coefficients for black and other. And so black and other here are going to be in reference to the omitted category, white. And so we can see that the net of their father's education, their age, and their sex, this coefficient, the negative 1.8, is in comparison to white. And it tells us the blacks have, on average, about 0.18 years of education less than whites. Although there's no star next to it, indicating that this result is not statistically significant. Therefore, it could happen by chance alone. And here's the effect of other races compared to white. We can see that other races have about 0.36 years of education less than whites, net of their effect of father's education, age, and sex. But again, this has no stars next to it, indicating that it's not statistically significant, which means that this could be something that's just happening by chance alone. It could be a function of this particular sample that we're using. It doesn't hold in the population. So basically, all the race coefficients were interpreted relative to white, the reference category, and they show the average difference in the predicted value of the dependent variable relative to the omitted reference category. So the black coefficient, again, was negative 0.18. We interpret that to say the blacks have 0.18 fewer years of education on average than whites, but the difference isn't statistically significant, which means it only holds in this sample. And we have the same interpretation for other. Okay, so let's close by talking about how we construct the proper regression model. So what variables should be included in the model and what shouldn't? And so basically, you can think of it in the following way. Any variable that we don't include in the model is left in something called an error term. And the error term is basically what includes the effects of all unmeasured variables. And so our goal is to isolate some variable that we've included in the model that we're most interested in. And so we're trying to isolate the effects of those variables from each other and from anything that we've left unmeasured. Therefore, what we're trying to do basically is to include any variables that affect our outcome, our dependent variable, that are also systematically correlated to the independent variables that we're most interested in. And so using those two criteria, we should basically include all those variables that have, in this case, some kind of effect on education. And let's say that we're most interested in the effect of father's education, and variables that are also systematically in some way related to father's education. And so, for example, if we thought that mother's education was something that was systematically related to father's education and also influenced the respondent's education, we should control that, because controlling it would give us the effect of father's education net of that variable, and it would help to isolate it, and it would tell us basically how much the father's education influences respondent's education, net of other things that could affect both the father's education and the respondent's education, therefore avoiding spurious relationships.